Hello viewers, it is indeed a great pleasure for me to bring to you another program in the Teleschool Senior Series. The subject today is the normal probability distribution. In fact, we have devoted 2 programs to this topic. In the first program, we have seen how to use the normal probability distribution, how to use the table, what is the standard normal variable. In this program, we are going to show to you how to use the process of standardization. However, we have also included a brief review of the first program. So let's see the normal probability distribution, part 2. Now, if x is a continuous random variable which follows a normal distribution, then we are going to write it in mathematical notation as follows, where x is the normal variable, n represents the normal probability distribution, the symbol mu stands for the mean value of x, sigma square is this variance of x, whereas sigma is the standard deviation of x. The normal curve is shown as follows. So mu is the mean value of x. The normal curve is symmetrical about the mean value of x. Let's now review the properties of the normal variable. If x is a normal variable, and fx is the probability density function of x, and this is the normal curve, mu is the mean value of x, then we'll write in mathematical notation that x follows a normal with mean mu and variance sigma square. The distribution is symmetrical about the mean value mu. For a normal distribution, the mean, the mode, and the median have the same value mu. The range of value of x is from minus infinity to plus infinity. And what is more important is that the total area under the normal curve is equal to 1 unit. Suppose that you need to evaluate the probability that the probability associated with a normal distribution. Then, in order to obtain the values of the probabilities, you will have to evaluate the area under the normal curve. Let's consider the distribution of mass of Mauritians. Suppose that the mean mass of a Mauritian would be 60 kilogram, and that the mass follows a normal probability distribution. We are interested to know, if we choose a Mauritian at random, what is the probability that the mass of that Mauritian would be less than 40 kilogram. So let's see. The horizontal axis represents the mass of a Mauritian, and suppose that the mean mass of a Mauritian is 60 kilogram, and that the mass of a Mauritian follows a normal distribution. Suppose that we want to know the probability that the mass of the Mauritian is less than 40 kilogram. We start by locating the 40 kilogram on the horizontal axis, drawing the vertical line joining 40 kilogram on the horizontal axis to the normal curve, and then shading the area. This shaded area represents the probability that the mass of a Mauritian chosen at random will be less than 40 kilogram. Let's take another example. Suppose that we choose immersion at random, and we would like to know what is the probability that the mass of the immersion would be between 55 and 65 kilogram. Let's see. The horizontal axis again represents the mass of immersion. The mean mass is 60 kilogram. If we want the probability that the mass of the immersion lies between 55 and 65 kilogram, then we start by locating 55 and 65 on the horizontal axis, drawing the vertical lines joining these values to the normal curve, and then shading this region. This shaded area would be equal to the probability that the mass of immersion would lie between 55 and 65 kilogram. If we want to find the probability that the mass of a chosen immersion is greater than 85 kilogram, then again we start by locating 85 kilogram on the horizontal axis, drawing the vertical line joining 85 to the normal curve, and then the area to the right would represent the probability. Of course, we cannot use the usual techniques of integration to evaluate these areas. As you have noted, the normal curve has a bell shape, and the equation of the normal curve is quite involved. Therefore, we would use statistical tables to evaluate the area. Unfortunately, the statistical tables do not provide the values of area for all normal curves. It provides area only for the standard normal curve. So let's see what is the standard normal variable and the standard normal curve. The standard normal variable is represented by the letter Z. Fx is the probability density function of Z, and this is the standard normal curve. Z is the normal variable, N stands for the normal probability distribution. The mean value of Z is 0. The mean value of Z is 0, whereas the variance of Z is 1. So this is the standard normal curve, and Z is the standard normal variable, and the properties would include mean value of Z is 0. The standard deviation of Z is 1, and the variance of Z is also 1, but you write it as 1 square. In the same way as we have calculated the area under the normal curve representing the mass of immersion, we will calculate the area under the standard normal curve. But remember, the value of the area will be obtained from the standard normal table. So this is the z-axis, the mean value mu, which is 0. Suppose that we want to calculate the probability z is less than equal to a. We use the symbol phi a to represent probability z less than equal to a. As usual, if I want to calculate the probability that the value of z will be less than or equal to a, I locate a on the horizontal axis and then draw the vertical line joining a to the curve and then shade the area. So this shaded area represents the probability z less than or equal to a, and its value is represented by phi a. As we said, the total area under the normal curve is 1. Therefore, the unshaded area would represent the probability z greater or equal to a, and this would be written as 1 minus phi a. So probability z less than or equal to a is represented as phi a. Probability z greater than or equal to a is equal to 1 minus phi a. We summarize the properties of the standard normal variable here. Probability z less than or equal to a is same as the probability z is less than or equal to a, because z is a continuous random variable and it is phi a. Less than or equal to, it is phi. Probability z greater than a, which is equal to z greater or equal to a, is 1 minus phi a. Greater than or equal to, it is 1 minus phi a. Probability that z will lie between a and b is given by phi of b minus phi of a. Now we're going to show to you how to use the standard normal table. Remember, the values in the standard normal table will give you the area under the standard normal curve. The standard normal curve has a mean value, is symmetrical about the mean value 0, and we represent the standard normal variable by the letter z. The normal table mainly consists of 4 parts. The first part, in the first column, we have the value of z, the first decimal point in the value of z. In the top row, we have the second decimal point of z, and in the next part, the third decimal point of z. And in the remaining part of the normal table, we have the values of phi. So the first column would contain the unit and the first decimal point in value of z. 0.1 means 0 unit in value of z, and the first dp is 1 in value of z. Here, 2 means that it is the second decimal place in the value of z. 3 is also the second decimal place in the value of z. 1 is the third decimal place in the value of z. 2 is the third decimal place in the value of z. 9 is the third decimal place in the value of z. So the values of z are written in the first column and the top row. The remaining values are values of phi. So we are going to show to you how to use the normal table to evaluate one value of phi. Suppose that we have to evaluate phi of 1.84, which means we want to find the value of phi when z is 1.84. So 1.8 would be located in the first column, and then the second dp in the value of z will be located in the top row, and the value of phi would be read here. The value of phi is 0.9671. Therefore, the value of phi is 0.9671. Remember that phi of 1.84 is in fact probability z is less than or equal to 1.84 is 0.9671. We'll take another example to show to you how to evaluate phi when we have in the value of z a non-zero value of the third dp. Suppose that we have to find the value of phi of 0.123. So first of all, we'll locate 0.1 in the vertical column, in the first column, 0.1. Then the second dp would be located in the top row, first part of the top row, which contains the second decimal places in the value of z. The value of phi here is 0.5478. 0.5478. That is, phi of 0.12 is 0.5478. But we need phi of 0.123, where 3 is the third dp in the value of z. So we locate the value of phi corresponding to the third dp of z, which is 12. This 12 is in fact added to the last 2 dp in the value of phi. Adding the two gives you 0.5490, which means that the value of phi of 0.123 is 0.5490. Very often, the value of phi is given to you, and you have to use the reverse process to find the value of z. Let's see how to find the value of z when the value of phi is given. Suppose that the probability z less than or equal to a is phi a, and the value of phi of a is b. Then a would be given by phi inverse of b. Let's take an example to illustrate how to find phi inverse. Suppose that you are given that phi of a is 0.9699 and you are told to find value of a. Of course, value of a would be given by phi inverse of 0.9699. So in order to find the value of phi inverse of 0.9699, we locate this value 0.9699 in the normal table, and then read horizontally the value of z in the first column, which is 1.8, and read the second dp in the value of z in the top row, which is 8. So we will say that phi inverse of 0.9699 is 1.88. Let's take another example to find the value of phi inverse. And in this case, we will use an example in which we'll also be using the third decimal place in the value of z. Suppose that you're told phi of a is 0.95 and you're asked to find the value of a. Of course, the value of a would be phi inverse of 0.95. We'll start by locating 0.95 in the table, and we find that 0.95 is not there in the table. So in this case, you would take a value which is closest to 0.95 but less than 0.95, and we find that such a value is 0.9495. As in the previous example, we'll read horizontally to find the value which we need to add to 0.9495 in order to get 0.9500. Of course, we need to add a value of 5 to 0.9495 in order to get 0.9500. So now we will read the value of z. It corresponds to 1.6. The second dp in z is 4, and the third dp is 5. Therefore, phi inverse of 0.9500 is 1.645. So remember, if a value of phi does not exist, we always take a value of phi which is smaller but closest to it. Then we find in the third column, which is the value that we must add to this value of phi in order to get the value of phi that we wanted and which doesn't exist. After doing that, we simply read the value of z in the first column, the second dp in the top row, and the third dp in the top row, in the second part of the top row. So in this case, phi inverse of 0.95 is 1.645. Now we'll see how to standardize the normal variable. That is, if x follows a normal probability distribution with mean mu and variance sigma square, how to transform it into z, which is the standard normal variable with mean 0 and variance 1. Now, why do we need standardization? Standardization is important whenever you are evaluating probabilities involving x. As I said, that the normal table which we have just seen will give you the value of the area under the standard normal curve. So if you want to evaluate probabilities and hence area involving x, you will need to transform x by the standardization process. That is, we standardize x first into z and then use the standard normal table to find the probabilities. So, to standardize x, first of all, we subtract from x the mean value of x, that is x minus mu, and then divide this difference by the standard deviation of x. So this is the transformation which transforms x into z, x minus mu over sigma. Now, suppose that you have to find the probability x is less than or equal to a, then after standardization we will have probability z less than or equal to a minus mu, which is the mean value of x, divided by sigma. And in terms of phi, since we have less than or equal to, it is simply phi. So probability x less than or equal to a becomes, after standardization, z less than or equal to a minus mu over sigma. And when this is written in terms of phi, since we have less than, it becomes phi simply. Phi can be found from the standard normal table. Suppose that we have probability x greater or equal to a, then after standardization this becomes z greater or equal to a minus mu divided by sigma, and since we have greater than or equal to, it becomes 1 minus phi. The phi can be evaluated from the standard normal table. We're going to take a problem where we will use the standardization process. Let's see. An industrial process produces a large number of items whose weights are normally distributed with mean 18.5 kilogram and standard deviation 1.5 kilogram. We want to find the probability that an item chosen at random weighs more than 21.5 kilogram. Note that here the first question we ask ourselves, what is normally distributed? It is the weight of the items. What is the mean value of the weight? 18.5 kilograms. What is the standard deviation? 1.5 kilogram. And we are interested in knowing the probability that an item chosen at random will weigh more than 21.5 kilogram. So first of all, we have to introduce the variable x, which is mass of an item, and mass of an item follows a normal distribution. The mean value was given in the question 18.5 and the standard deviation 1.5. We were requested to find the probability that x is greater than 21.5. After standardization, probability x greater than 21.5 becomes z greater than 21.5 minus the mean value 18.5 divided by the standard deviation. Simplifying 21.5 minus 18.5 over 1.5 will get 2. So probability z is greater than 2. Remember, we were asked to find the probability x is is greater than 21.5 kilogram. We standardize it by subtracting from this value the mean and dividing by the standard deviation. We get probability z greater than 2. So z greater than 2, since we have greater than, it becomes 1 minus phi of 2. Phi of 2 can be found from the table to obtain 0.227. So the probability that an item weighing more than 21.5 kilogram would be given by the probability x greater than 21.5, which after standardization produces probability z greater than 2, written in terms of phi, 1 minus phi of 2. Evaluating it from the table gives 0.227. We'll take another example to illustrate to you how to use the process of standardization. Let's see. A manufacturer knows from experience that the resistance of resistors he produces is normal with mean 100 ohms and standard deviation 2 ohms. What percentage of resistors will have resistance between 98 ohms and 102 ohms? So the first thing that we must note is which is the variable which follows a normal distribution. It is the resistance of the resistors which follows a normal distribution. The mean value has been given 100 ohms and the standard deviation 2 ohms. So let's see the solution. In the question we were told that the mean value of the resistance is 100 ohms and the standard deviation of the resistance is 2 ohms. We were requested to find the probability that the resistance would lie between 98 and 102 ohms. So in order to find this probability, we need to standardize by using the standardization transformation. So we need to standardize the variable x and then transform the numbers 98 and 102 by using this transformation. Transforming 98 by subtracting the mean from it and then dividing by the standard deviation 2 ohms gives us minus 1. Transforming 102 minus the mean 100 ohms and then dividing by the standard deviation gives us plus 1. Therefore, the probability that x lies between 98 and 102 after the process of standardization will give us the probability that z will lie between minus 1 and plus 1. So, in fact, we have to find the probability that z will lie between minus 1 and plus 1. This would be given by phi of 1 minus phi of minus 1, which is 0.6826. Now, another way to interpret this result would be to say that the percentage of resistors having resistance between 98 and 102 ohms is 68.26%. So we have 68.26% of the resistors produced by the manufacturer have value between 98 and 102 ohms. We'll take a last example in which we are going to show to you how to evaluate the value of the mean and the standard deviation when they are unknown. That is, in the question, the value of the mean and the standard deviation are not given. Instead, the value of the probabilities are given. We are going to use the values of the probabilities to evaluate the value of mean and standard deviation. So, let's take the following example. The lifespan of batteries is known to follow a normal distribution. 11.55% of them last for more than 20 hours and 5.89% last for less than 10 hours. Calculate the mean and standard deviation of the distribution of the lifetime of the batteries. Note that we have to calculate the mean and the standard deviation. We are given the two probabilities, that is 11.55% of the batteries last for more than 20 hours and 5.89% last for less than 10 hours. Note that it is the lifespan of the batteries, lifetime of the batteries, which follow a normal distribution. So first thing that we will do is to define X as the lifetime of the battery. X follows a normal with mean mu and sigma square. Both are unknown. First statement in the question was 11.55% of them last for more than 20 hours. This means that the probability that the lifetime is more than 20 hours, that is X is greater than 20, is 11.55% or 0.155. So of course we cannot work with this probability, we need to standardize it. To standardize, we'll replace X by Z, of course, because we are transforming X into Z. How? By subtracting from this value the mean mu and dividing it by the standard deviation. Of course, these two remain unknown, and writing it in terms of phi, since we have greater than, it will become 1 minus phi of this value, which is 0.1155. After writing the equation, we need to make phi the subject of the equation. So let's see. Phi of 20 minus mu over sigma would be given by 0.8845 by transferring the 1 on the other side and dividing by minus 1, we get 0.8845. Now we need to have an equation containing mu and sigma, so we'll take phi inverse. So that 20 minus mu over sigma is phi inverse of 0.8845, and which we have obtained from the table as 1.198. Cross multiplying gives us 20 minus mu is equal to 1.198 sigma. So this is our first equation which will help us to obtain the value of mu and sigma. The second statement in the question was 5.89% of the batteries last for less than 10 hours. What does this mean? This means that the lifetime of the batteries were 5.89% of the batteries had a lifetime less than 10 hours. So the probability X less than 10 is 5.89%. Therefore, after standardization, Z would be less than 10 minus mu over sigma, which is 0.0589. Again, writing it in terms of phi, since we have less than, it is phi directly, so phi of 10 minus mu over sigma is 0.0589. Again, we'll have to cross multiply in order to obtain an equation containing mu and sigma. Here we have cross multiplied, transferring the sigma on the other side to obtain the equation 10 minus mu is equal to minus 1.564 sigma. So this will be our second equation involving mu and sigma. Solving the two equations, one gives us mu is equal to 15.66 hours and sigma is equal to 3.62 hours. So viewers, This brings us to the end of today's program. In this program, we have seen how to use the standardization process in order to calculate the probabilities involving x which does not have a mean of 0 and standard deviation of 1. We use the standardization process in order to be able to calculate the probabilities using the standard normal table. Thank you for watching us. Until next time, it's goodbye from us.